In the current ever-evolving era of AI, there are numerous architectures for convolutional neural networks, each with its own advancements and nuances, and for beginners I know that navigating this vast landscape can feel overwhelming. That's why, in this video, I'm taking you on a journey through the history of CNNs, from their early beginnings to the cutting-edge models we use today, and we'll explore the key breakthroughs that shaped the evolution of this field, making it accessible and exciting for everyone. So now let's explore how convolutional neural networks have evolved over the years. Now I think it's safe to say that we're all familiar with the conventional CNN architecture, where the first layers learn simple patterns like edges and gradients using convolutional filters, and as we go deeper in the network, the layers learn more and more complex features. But did you know that this idea or this concept was first introduced in a model called the neocognitron? So let's take a trip back in time to the early days of computer vision, specifically in the 1980s. This is where the story of convolutional neural networks really begins, with a groundbreaking invention called the neocognitron, created by Kunihiko Fukushima in 1980. Actually, this model is not a conventional CNN, meaning it does not rely on convolutional filters to learn patterns. However, it introduced ideas and concepts that were adopted later on in traditional CNN architectures. Now, this model was inspired by something truly incredible, and that is the way animals' brains process what they see, particularly through simple and complex cells in the visual cortex. And based on that, Fukushima's neocognitron introduced two game-changing ideas. The first one is the local receptive fields, and the second one is the hierarchical feature extraction. These concepts would later form the foundation of CNNs as we know them today. It also marked one of the earliest uses of convolutional-like filters through its S-layer, although these filters weren't exactly the same as those found in modern CNNs. The architecture introduced by Fukushima was really innovative and ahead of its time. It was built with alternating layers of what he called S layers for simple cells and C layers for complex cells. A couple constituted of an S layer followed by C layer is called a stage, and the whole neocognitron network is constructed of 3 stages. This layout is very similar to what we see in early CNN architectures. The S layer worked like detectors, identifying basic features like edges and corners through small localized connections. Meanwhile, the C layers played the role of translators, taking these simple features and generalizing them, creating a form of translation invariance, meaning the model could recognize an object even if they shifted or moved slightly. And these layers were doing something revolutionary. First, the S layer used local receptive fields with connections that resembled convolutional filters because they were responsible for detecting simple features like edges within a localized region of the input, while the C layers performed a pooling-like operation to reduce the spatial size, helping the model understand spatial hierarchies. And as we go deeper in the network, the neurons at deeper layers are connected to a broader region of the input image, which results in a progressively layer-effective receptive field and more complex and abstract recognized patterns. So this was the first stone in what would become the towering structure of modern CNNs. And maybe without it, the AI that powers so much of what we see today might look very different. However, this architecture had its limitations, obviously. One significant drawback was its lack of learning algorithm like backpropagation. At that time, backpropagation hadn't been widely applied in neural networks. It wasn't until the mid-80s, exactly 86, when Rumelhart, Hinton and Williams popularized it, that neural networks became more efficient in learning. And naturally, without backpropagation, the neocognitrons filter were manually designed or adjusted using heuristics rather than being learned from the data. This not only made the model more rigid, but also limited its adaptability to different tasks, requiring manual adjustments for new vision problems. It also highlights how important advancements like backpropagation were in unlocking the full potential of neural networks. Now jumping forward to 1989, a major breakthrough occurred with the introduction of LeNet-1. Created by Yann LeCun and his team, LeNet-1 was one of the first convolutional neural networks to be successfully applied to real-world tasks, The model's architecture consisted of a single convolutional layer, followed by a subsampling or pooling layer, which performed average pooling to downsample the input. This process was crucial for reducing computational complexity and helping the model generalize by focusing on essential features. LeNet 1 introduced the concept of weight sharing, where the same kernel or filter was applied across the entire input image to detect features. And this seemingly simple or obvious idea reduced dramatically the number of parameters compared to fully connected layers. Another key innovation was the use of trainable filters that learned the best features through backpropagation, which is the famous supervised learning algorithm that uses gradient descent to minimize the error during training. The original model used a hyperbolic tangent activation function, which helped with nonlinear learning and faster convergence, although it suffered from the infamous vanishing gradient issue. And to summarize it, basically when training a neural network or convolutional neural network, the gradients that are used to update the weights are calculated through the mathematical chain rule formula in the backpropagation algorithm. This formula states that the derivative of a composition of two differentiable functions is given by the following product, so moving backward from the output layer to the input layer. In deep networks, the gradients often become very small as they are propagated through many layers. And in case of a 10H activation function, we can get very small gradient values. Such values are multiplied in the chain rule formula, so they get smaller and smaller until vanishing. This issue slows down the learning dramatically, and in deeper network, it could stop the training process altogether. Now, this issue was resolved upon subsequent CNN architectures, and we'll see later the main techniques used as a remedy. Now, going back to the LeNet 1 architecture, it had fully connected layers at the end, which combined the learned features from the earlier layers to classify digits, and it achieved impressive results on tasks like handwritten digit recognition. Nearly a decade later, in 1998, the improved version called LeNet 5 was presented by Yann LeCun and his team, building upon the foundation laid by LeNet 1. LeNet 5 was designed to handle more complex tasks with higher accuracy, specifically handwritten digit recognition for the MNIST dataset. The architecture of LeNet 5 was more advanced, featuring two convolutional layers, C1 and C3, each followed by subsampling or pooling layers, S2 and S4, which performed average pooling. These layers helped the network learn increasingly complex hierarchical features while keeping the computational cost manageable. LeNet 5 also introduced three fully connected layers, F5, F6, and the output layer, which allowed for more intricate feature combinations and higher classification power compared to LeNet 1. One of the key improvements in LeNet 5 was the use of more convolutional layers, meaning more trainable filters, and that made the model more capable of learning fine-grained features from the input data. Another notable innovation was the introduction of backpropagation with weight sharing for deeper architectures. LeNet 5 achieved impressive accuracy for its time, where it reached 1% error rate on the MNIST dataset, and that alone demonstrated that CNNs could be applied beyond research experiments. Although the results with LeNet 5 were really impressive, the architecture of neural networks at that time remained shallow, which didn't allow for versatile real-world applications. From 1998 to 2012, there was no groundbreaking shift in CNN architectures, but that period was anything but empty. It was a vibrant time of exploration and experimentation. Researchers were busy applying CNNs to diverse challenges like face detection and speech recognition, opening new doors for what these networks could achieve. Also, the rise of larger datasets and early GPU implementations started to reveal the true potential of CNNs. All of this set the stage for the game-changing moment that came with the introduction of the AlexNet in 2012. And we can say that the introduction of the AlexNet architecture sparked a revolution in deep learning and computer vision. So the AlexNet architecture, developed by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, was trained on the ImageNet dataset containing over 1.2 million labeled images across 1,000 categories. AlexNet drastically reduced the top 5 error rate from 26% reached in 2011 to 16.4% in the ImageNet Large-Scale Visual Recognition Challenge in 2012. and that really caught the interest of many researchers in the AI field. Now, several key innovations in the AlexNet architecture contributed to its success. The first one is that it used a rectified linear unit activation function, or ReLU for short, which replaced the traditional sigmoid or 10H activation functions. Now, this change alone helped addressing the vanishing gradient problem by allowing gradients to propagate more efficiently, and that also helped making the training process much faster. AlexNet also introduced dropout, a regularization technique that randomly drops out a portion of neurons during training, forcing the network to avoid overfitting by preventing reliance on specific neurons. This was critical given the size and complexity of the network, which made it even more prone to overfitting. Another important feature of AlexNet was its GPU acceleration. AlexNet was trained using two NVIDIA GTX 580 GPUs, which allowed the model to be trained in parallel, and that greatly sped up the process. This was one of the first time GPUs were used for deep learning at scale, enabling networks to grow deeper and larger than ever before. And to put that into perspective, without GPU acceleration, training the AlexNet architecture on the ImageNet dataset would have taken weeks instead of days. The architecture of AlexNet consisted of 5 convolutional layers, each followed by a max pooling layer, which reduced the spatial dimensions of the feature maps while retaining important features. It utilized kernels of various sizes, 11, 5, and 3. The network also had 3 fully connected layers at the end, which combined the extracted features for a final classification. Another innovation in the AlexNet was the extensive use of data augmentation, applying random transformation like horizontal flipping, cropping, and color changes to artificially expand the training set, improving the network's ability to generalize. Now, jumping forward to 2014, another great architecture was introduced, the VGGNet. Developed by the Visual Geometry Group at Oxford University, it introduced a simpler but deeper architecture. The VGGNet used very small 3x3 convolutional filters throughout the whole network, which was a deliberate choice to reduce the number of parameters while increasing the network depth. And with these small features, the VGGNet stacked many convolutional layers to extract fine-grained details from the input images. The model's depth varied between 16 and 19 layers, making it much deeper than AlexNet and achieving a much better result on the ImageNet dataset. While the VGGNet's architecture's simplicity was one of its strengths, it required a large number of trainable parameters due to the depth of the network, and that made it computationally expensive to train and deploy. But despite this, the VGGNet demonstrated the effectiveness of deeper network in the extraction of complex and hierarchical features. Its impact was so significant that the idea of stacking small filters became a standard design principle for CNNs in the years that followed. Also in 2014, GoogleNet, also known as the Inception Network, introduced a revolutionary idea with Inception modules. These modules allowed for efficient computation by performing multiple convolutions of different kernel size, 1x1, 3x3, and 5x5 in parallel within the same module. The main innovation was that by using convolutions of various sizes, the network could capture features at different scales, from fine details to more global patterns, all within the same layer. This approach was key to making the model computationally efficient while retaining high accuracy. In addition to these parallel convolutions, Inception modules included 1x1 convolutions for dimensionality reduction, helping to decrease the number of parameters and making the model lighter and faster to train. This allowed GoogleNet, despite its 22 layers, to use about 110 million parameters less than models like VGGNet and achieve similar accuracy. It was obvious at that time that deeper networks would perform better, and this was hinted in the Inception paper with the famous "We must go deeper" meme from the movie Inception. Even though the Inception network improved a lot over the family of VGG networks, it didn't really present an efficient way to go much deeper, and that's mainly because of the vanishing gradient problem that would arise with deeper networks. And on top of that, with deeper architectures, the network tends to somewhat forget the early patterns learned in early layers. However, only 1 year later, the residual network, or ResNet for short, completely transformed the landscape of deep learning by solving one of the most challenging problems in training deep networks, which is the vanishing gradient problem. It was developed by Kai-Ming He and his team. ResNet addressed the issue with the introduction of skip connections or residual connections. These connections allowed the network to bypass one or more layers by adding the input directly to the output of a deeper layer, effectively creating a shortcut. Now, the key insight behind ResNet was the idea of residual learning. So instead of each layer learning the full transformation, it only needed to learn the residual or difference between the input and output. This made it easier to train very deep networks because the gradients could flow more freely through the skip connections, allowing for the propagation of error signals during backpropagation. The introduction of skip connections not only mitigated the vanishing gradient problem but also reduced the risk of overfitting by encouraging the network to learn simpler and more incremental updates. The ResNet architecture demonstrated very effectively that deeper networks could actually perform much better if trained correctly. In fact, the team was able to successfully train networks with 152 layers, achieving state-of-the-art performance in the 2015 ImageNet competition. Now, as models grow deeper and more complex, more efficiency was crucial, and in 2016 we see the emergence of exception or extreme inception, a model developed by François Chollet. Exception was a significant leap forward in the evolution of the inception architecture. Its core innovation was the use of depth-wise separable convolutions. This technique separated the standard convolution operation into two parts. First, a depth-wise convolution which applied a single filter per input channel, and second, a point-wise convolution which used one-by-one convolution to combine the outputs across channels. Exception consisted of 71 layers and has approximately 22 million parameters, making it significantly lighter compared to traditional models. The depth-wise separable convolution helped exception strike a balance between efficiency and accuracy, allowing the model to outperform traditional inception networks on benchmark like ImageNet, achieving a top 5 accuracy of 94.5% without a significant increase in resource consumption. Next, in 2017, the DenseNet or densely connected convolutional networks introduced a novel approach to skip connections, which enhanced the gradient flow and information reuse. Unlike ResNet skip connections, which only connected layers a few steps apart, DenseNet connected each layer to every subsequent layer. This meant that the feature maps learned in earlier layers were directly reused by all subsequent layers, ensuring that no information was lost as the network deepened. This dense connectivity pattern had several advantages. The first one, it facilitated better gradient propagation, reducing the risk of vanishing gradients in very deep networks. Additionally, DenseNet achieved more efficient parameter usage because each layer reused the features learned by its predecessors, eliminating the need to relearn redundant features. As a result, DenseNet required fewer parameters than traditional CNNs, while still maintaining high performance. The architecture was particularly effective for tasks that required fine-grained feature extraction, proving that dense connections could enhance both accuracy and efficiency. In the same year, squeeze and excitation networks, or SENets, emerged as a significant advancement in convolutional neural networks architectures by introducing the innovative squeeze and excitation block, which enhances the model ability to focus on the most informative features. The key innovation in SENets lies in their capacity to adaptively recalibrate channel-wise feature responses. This is achieved through a two-step process. First, the network squeezes the global spatial information into a channel descriptor using global average pooling, effectively capturing the overall context of each channel. Then it excites these descriptors through a learned fully connected layer that generates a set of weights, highlighting important features while suppressing less relevant ones. By incorporating SE blocks into existent architectures, SENets have demonstrated substantial improvements in performance across various vision tasks and reached state-of-the-art performance. 1 year later, in 2018, EfficientNet, developed by Google researchers, tackled the challenge of model scaling by introducing a method called compound scaling. Traditional CNNs often scaled by increasing depth, that's the number of layers, or width, which is the number of channels per layer, in a manual fashion. However, the introduced efficient net architecture approached this problem systematically by simultaneously scaling along 3 dimensions, the depth, width, and input resolution, in a balanced way. EfficientNet B7, the largest variant, has 66 million parameters and achieves a top 1 accuracy of 84.3 on ImageNet, making it one of the most accurate models of image classification at that time. EfficientNet utilized the predefined compound scaling coefficient to uniformly adjust these dimensions based on a fixed ratio, and that coefficient was optimized using a simple grid search technique. Its main purpose is to ensure that the network could grow in capacity without unnecessary complexity. This made it possible to scale up or down the model depending on the available computational resources, achieving a superior performance with fewer resources compared to conventional scaling methods. Another significant advantage of EfficientNet is its use of MB-Conv blocks, that stands for Mobile Inverted Residual Bottleneck Convolution, which incorporate depth-wise separable convolution and skip connections. This design reduces computational costs while maintaining high accuracy, making EfficientNet models particularly suitable for scenarios where efficiency is essential, such as mobile and edge devices. Now, until 2019, the computer vision field was dominated by convolutional neural networks, and they held the state-of-the-art performance across all the computer vision tasks. But that year we witnessed a paradigm shift in the field of computer vision with the introduction of Vision Transformer. Although we're talking about convolutional neural networks, the introduction of Vision Transformer impacted the development of several subsequent convolutional neural networks, and we'll see examples of that. So the Vision Transformer brought the transformer architecture to the computer vision field. The transformer architecture was developed in 2017 for natural language processing. So the main innovation in Vision Transformer, or VIT for short, was its ability to process images in a completely different way from CNNs. And here's a quick overview of how it works. First, each image is divided into a grid of fixed size patches, which are then flattened and linearly embedded into patch tokens. These tokens are treated in the same manner as words in an NLP model, allowing the transformer's self-attention mechanism to operate on the entire image as a sequence of tokens. Unlike CNNs, which rely on convolutions and local receptive fields to capture spatial hierarchies, the VIT's architecture didn't rely on hierarchical structure of CNNs, which extract features layer by layer, but instead processed the image in one sweep, making it highly effective for certain vision tasks. Despite this, VIT required large amount of labeled data for training, and it initially outperformed CNNs primarily in settings with abundant training data, such as the ImageNet 21K dataset. However, CNNs were far from obsolete. In 2021, the Swin transformer emerged as a model that combined the strengths of CNNs and transformers, taking the best of both worlds. The Swin transformer applied self-attention mechanism with local windows rather than across the entire image, and by using window-based self-attention, Swin Transformer retained the efficiency and locality of CNNs while still benefiting from the transformer's ability to capture global dependencies. The innovation of Shifted Window Transformer, or Swin Transformer, was how it handled the transition from local to global. It used a hierarchical structure where each stage processed progressively large windows of the input image. And as the model advanced, it merges patches into larger ones, creating a pyramid-like structure, similar to the CNN's feature maps, where the low-level details are captured in early layers and higher-level abstractions in later layers. This allowed the Swin Transformer architecture to reach state-of-the-art performance on a variety of computer vision tasks. Jumping forward to 2022, the release of Conv by Zhuang Liu and his team marked a significant revisitation of the traditional CNN architecture, integrating modern ideas from transformer-based models. Conv aimed to optimize CNNs by incorporating elements like layer normalization, which helps stabilize and accelerate training by normalizing the output of each layer, This was particularly beneficial in deeper networks, where training can become unstable. So briefly, layer normalization, as described in its introduction paper, is a transposed batch normalization that computes the normalization statistics for each training case separately, rather than across a batch. This makes layer normalization particularly useful for recurrent neural networks and transformers, where inputs can vary in size and structure. But an adapted version of layered normalization is employed in Conv to account for the unique characteristics of image inputs. Additionally, Conv incorporated depthwise convolution, an efficient operation borrowed from architecture like exception mobile net and efficient net, which significantly reduced the number of parameters while maintaining high performance. Through these refinements and simplified design choices, Conv managed to push the boundaries of CNNs, proving that they still can compete with transformer models in modern computer vision tasks. From 2020 onwards, transformer-based architectures such as vision transformers, wind transformer, and data-efficient image transformers have established themselves as the state-of-the-art in image classification tasks. However, despite this shift, CNNs continue to be widely used across various applications. They primarily serve as effective feature extractors due to their established performance and efficiency. To further enhance CNN capabilities, several innovations have emerged. First, we have RexNet, which introduces a new efficient building block design that enhances representational power while reducing computational costs. Then we have the NFNets, which eliminates the need for normalization layers, and it used a gradient clipping technique instead to achieve a stable and efficient training. Then we have the MogaNet. The main innovation in MogaNet is its special way of paying attention to different parts of the image, called multi-granularity attention mechanism. You can imagine it as if the MogaNet can look at the image in different levels of details. It can zoom in on small details as well as take a step back to see larger, broader features. And while the concept of attention is borrowed from transformers, MogaNet utilizes it within the framework of convolutional neural networks to improve its performance on image tasks. These latest advancements illustrate the ongoing evolution of CNN architecture, ensuring their relevance in the ever-changing landscape of deep learning. So there you have it, a journey through the evolution of convolutional neural networks. From the neocognitron in 1980 to today's hybrid models, the CNN architectures evolved dramatically, and along the way we've seen key innovations like skip connections and depthwise separable convolutions, and also residual learning. All of these innovations have shaped how we solve computer vision tasks. From facial recognition to medical imaging and also autonomous driving cars, CNNs continues to evolve, and it's really exciting to see where the future takes us. So I hope you found this video helpful and informative. Thanks for watching, and see you in the next one.